how memory is released. In particular, we're going to dive deep into how a mechanism called garbage collection works behind the scenes in order to keep our memory clean and healthy. So remember how in JavaScript, each value that we create goes through a memory lifecycle where first, memory is allocated for the value, then the allocated piece of memory is used, and finally, when no longer needed, the piece of memory is released. Now, we already talked in depth about step 1. Step 2 is pretty obvious, so there's actually nothing to learn there. And so let's now turn our attention to the way in which memory is released in the JavaScript engine in step 3. So basically, we're going to answer the question, how is memory freed up after we no longer need a certain value? Now, since these values are stored in the stack and the heap, we need to analyze both these storage mechanisms. So first off, in the call stack, it's all very simple, because the variable environments where primitives are stored are simply deleted when the corresponding execution context pops off the stack. So as an example, here is the call stack with the global execution context and 2 additional ones for 2 function calls. The global execution context has the x variable, which is clearly a primitive, and the execution context of the calc_h function has variables y and z. So these 3 variables are clearly stored in the call stack. And so then, as the execution context pops off the stack, the variable environment of the calc_h function will just be removed from memory together with the execution context that just popped off the stack. So as I said, very simple, right? Variables are simply stored in an execution context in a call stack, and as soon as the context is gone, so are the variables. And the memory that they occupied is simply released for future usage. Now, notice what happens with the x variable in the global execution context. Since this execution context never disappears, this value will stay in the stack forever. Now, this is no big deal. I just wanted to make it clear that global variables will, of course, never be deleted, which is pretty intuitive, I think. Okay, but now let's move on to the heap, where memory management is considerably more complex. So, in order to delete old, unused objects from the heap and free up memory, JavaScript engines employ a process called garbage collection. This garbage collection is the central tool for memory management in any JavaScript engine. And notice how I said engine here, because it's indeed the engine that runs garbage collection automatically whenever it sees fit. We developers cannot control when the heap memory is cleared by garbage collection, which is actually a great thing, because this automatic memory management makes our lives a lot easier. So you can basically think of garbage collection as an automatic cleaning service that comes into your house from time to time and identifies and removes old stuff that no one is using anymore. But anyway, there are different ways to implement garbage collection, but all modern engines use an algorithm called mark and sweep. And so let's now quickly check out how it works by bringing back the call stack and heap. Now, first of all, here in red and green, we have objects called hobbies and tasks, and so, as we just learned previously, these variables actually store references to the actual object stored in the heap. Let's now also say that the red object references some other object, which of course is also stored in the heap, and the green object references just another object. And by the way, I keep saying objects that are stored in the heap, but as we just learned earlier, these can actually be not just objects, but also arrays, functions, and other data structures like sets or maps. Okay, but now back to the mark and sweep algorithm. So the first step of garbage collection with the mark and sweep algorithm is the mark phase, where all objects that are reachable from a so-called root are marked as alive. Now, roots are basically starting points from which the algorithm starts to look for alive or reachable objects. And different things can be roots, but the most obvious ones are the global execution context, which is always present, and any other execution context of running functions. So again, the algorithm starts looking for objects in these places called roots. So in this example, the green and red objects are obviously alive, because they can be reached from one of the roots. And the same is true for the blue and gray objects. They're also alive because they can also be reached from one of the other reachable objects. But now let's take it one step further, because an object can be reached by more than just the global execution context or one of the other contexts in the stack. They can also be reached by event listeners or active timers, or by something that we call closures. And more about closures later. So these two are also roots for the mark and sweep algorithm. And now let's say that we have this purple object that is referenced and therefore reachable from an active timer, and this yellow object that is reachable from a closure. So both these are alive as well. And now finally, just to make this a bit more complete, let's imagine that we also have this pink object in the heap, which isn't being referenced by anything. And so this one is not marked as alive because it cannot be reached by any of the roots. So we can basically say that this one is dead. Okay, so with this, we basically just simulated the mark phase. So phase 1 in the mark and sweep algorithm. The second phase is the sweep phase, where all the unmarked objects, or in other words, all the unreachable objects, are simply deleted. Basically, the algorithm has decided in the first step that these objects are no longer needed, and that the memory occupied by them can be reclaimed and used for future memory allocations for future objects. So to simulate this in our example here, right now we only have one object that is unreachable, and that's the pink object. So what's going to happen in this phase? Well, that's right. The pink object will be deleted and the memory will be reclaimed. And so just like this, the automatic garbage collection has ensured that our memory stays nice and clean and not cluttered with objects that can no longer be accessed anyway, and that we therefore no longer need in the heap. Alright, but now what happens when the getTasks function finishes execution and its context pops off the stack? Well, let's simulate that our garbage collection runs again. And again, I want to just emphasize that there is no way to control or trigger garbage collection manually from our code. We also have no way of knowing when and how often garbage collection happens. It depends on a few factors, like how much memory our app is consuming, how much memory is available, which JavaScript engine the browser is using, and so on. But anyway, for the sake of this example, let's say the garbage collection algorithm runs again at this point. So now, with the getTasks variable environment gone, there's really no one to reference the green object anymore, right? Therefore, the green object and also the blue object are no longer reachable from any root. They're no longer alive. Therefore, as the process moves into the sweep phase, both the green and the blue objects will be swept away, and the memory that they occupied will be reclaimed. Okay, but now let's turn our attention to the red object, and let's ask ourselves the question, how could this object ever be deleted? Well, the answer is that it can't. The red object will never be deleted, so it will stay in the heap forever because the global execution context will never disappear. So this root will always exist and will always be able to reach the red object. This means that any globally defined object will never be garbage collected, even if we no longer need it in our code. And what about the purple and yellow objects? What if our app also no longer needs those objects? Well, this idea of an object being no longer needed actually brings us to our final topic of this lecture, which is memory leaks. So a memory leak happens when an object that is actually no longer needed by our application is incorrectly still reachable by the garbage collector from one of the roots. As a result, the object is marked as alive and is not deleted. Again, even though we actually no longer need it in our code. So it should be deleted, but it can't. And you can think of a memory leak basically like forgetting to throw away some stuff that you no longer need. And so this will then clutter up your house unnecessarily. But back to JavaScript, this happens when an object is still incorrectly referenced from somewhere. And one major source of these wrong and undesired references are alt and unnecessary event listeners and timers. If, for example, a timer creates an object, this object will always be reachable, unless the developer actively deletes the timer when they no longer need it. Otherwise, if the timer just stays around and keeps running, it will forever reference the unnecessary object, causing a memory leak. The same is true for an event listener that might no longer be needed at some point. So, in order to avoid memory leaks, make sure to always deactivate timers and event listeners when they're no longer required, especially if they reference large objects. Also avoid declaring large objects as global objects, because these will also never be garbage collected, as we just saw earlier. So that's going to lead to memory leaks as well. Now, memory leaks can be a huge topic, but there's no need to dig even deeper into it at this point. Alright, so this is a brief overview of how the garbage collection process works. It's going to run over and over inside the user's browser while they're using the application, making sure that memory stays clean and uncluttered of objects that are no longer necessary over time. Now, in reality, memory management is way more complex than just this. It's an extremely complicated process. There are actually multiple heaps, objects are moved from one heap to another depending on their age, the garbage collector has multiple algorithms for the different heaps, like generational garbage collection, and so on. But I'm absolutely sure that this broad overview that you just learned about is more than enough at this point. So this already gives you a great idea of how memory is automatically managed inside the engine. And now, before we move on, I need to quickly mention 4 more big topics about how JavaScript works behind the scenes that are not in this section, but closer to where we actually need to learn about them. The first one, which I actually just mentioned in the last slide, is closures. So we're going to dive really deep into closures once we reach the closer look at functions section. Next, one of the most fundamental concepts of JavaScript is prototypal inheritance, but we're only going to talk about that in the object-oriented programming section of this course, because it doesn't make sense to learn about this now, only to forget it all until we finally reach that section. The same is true for a detailed lecture on the event loop. We already introduced the event loop in this section, but in section asynchronous JavaScript, we'll dive really deep into how exactly this event loop works and why it's such a fundamental piece of the JavaScript engine. Finally, we'll have a few lectures on how the DOM actually works behind the scenes as well in the advanced DOM and event section, so that you can then apply what you learn right away. And with this, we actually finish this huge section about how JavaScript actually works behind the scenes. It was a pretty long one with so many new concepts to learn, and many of them were hard and probably confusing. But again, that's really not a problem. Hard and confusing concepts are always a part of learning, and even if you did not understand 100% of everything, you're still good to move on in the course to the next section now. Just reaching the end of this section already gives you a huge advantage over many other developers who have no idea about many of the things that I just showed you here. So congratulations for sticking with it to the end and for learning all of this valuable knowledge. And now with that, take a break, and I see you in the next section.